chapter for electric field and potential. We've already discussed the relation between electric field and potential, and also we have discussed the potential due to a dipole at an arbitrary point, which is given by V is equal to 1 by 4 pi epsilon naught p cos theta by r square. So this we've already done, where we have assumed this one to be the dipole, okay, and this is any point P at a distance r making an angle theta. So here the potential V is given by this particular expression which we have already derived in our previous lecture. Now moving ahead, again we will have to find out the field, the electric field due to a dipole, okay, at a particular point P making an angle theta, okay, at a distance r. Obviously what we'll do is that since field is a vector quantity, so it will have a radial component and a transverse component to that, which is say er and e theta, and the resultant of this two, it could be somewhere in between making an angle alpha with er, okay. So we'll just assume, or we'll just consider this point P to move slightly making an angle d theta, so that this distance will be given by r d theta, okay. So what we have done is that we have moved from P to new position Q, okay, and here we are having minus Q and plus Q. So this is the basic the diagram for finding out the field at this particular point. Now the electric radial component of the field is given by ER, and from the previous lecture we know the relation ER will be given by minus dV by dr, or along the direction, so it's partial derivative minus del V by del R, okay. So here we'll consider R to be variable and theta as a constant, okay. So theta will be treated as a constant term. So now we'll have we'll use this expression over here. So in the place of V we'll put over there, so it will be minus del 1 by 4 pi epsilon naught p cos theta by r square by del r. So what we'll have is this er equal to, okay, minus 1 by 4 pi epsilon naught. If we'll see over here, we have considered this one to be the constant term, so p cos theta will be, again it will come out from there, so we'll have del r to the power minus 2 by del r. Differentiating this, we'll have 2 p cos theta by 4 pi epsilon naught r cube. So this will be the the radial component, and likewise for the after the radial component we find out e theta, okay. So this e theta will be given by, again, minus del V by del R. In the place of del R, what we'll do is that we'll write minus del V, this R d theta, okay. So we'll substitute over here minus del V by del theta, and again in the place of V we substitute the same expression, and we consider R to be constant and theta as a variable, okay. So del 1 by 4 pi epsilon naught p cos theta by r square del theta. So the constant term will come out, so we'll have minus 1 by r 4 pi epsilon naught, again it will be r cube, okay, p del cos theta by del theta. So after differentiating this, we'll have p sin theta by 4 pi epsilon naught r cube. Here p, so here p is it's a dipole moment, okay. Now the resultant will be given by the, you can see from the diagram itself over here, perpendicular to each other. So the resultant E, this is E. Okay, so E will be given by E is equal to under root r square plus E theta square. Okay, so substituting the value of ER and E theta, okay, we'll get in this expression, we'll get something like this: 1 by 4 pi epsilon naught P by R cube under root 1 plus 3 cos square theta. Now, if we have to find out the angle, we'll do something like this. We have from this figure again, tan alpha will be equal to E theta by ER. Now substituting the value, okay, so substituting the value, we'll get the value of E theta and ER, we'll get half of tan theta. So alpha is equal to tan inverse half of tan theta. So this will be the angle actually. Now we can consider the different cases as we have done in the case of the dipole moment in the previous, potential due to the dipole moment. You can take theta equal to 0, theta equal to 90 degree, and just substitute the value of theta and 90 degree in this particular expression to get the value, resultant value. Okay, that is end on position and broadside on position. The next is the torque acting on a dipole. Torque acting on a dipole. We'll talk on this. If we place, this is the field, okay, the uniform field E, and you place a dipole, okay, of length 2d. Okay, this is plus q and this is minus q. The force acting on it will be along this direction and this will be along this direction. So the perpendicular distance is 2d and this is theta. This will be 2d sine theta. So this makes an angle theta. Okay, this dipole is inclined, making an angle theta with the direction of the field. So the torque will be given by force into perpendicular distance, that is EQ into 2d sine theta. Okay, so this tau is equal to E 2qd sine theta. So this 2qd is again P, so we have E, okay, P sine theta. So this could be written as P cross E, where P is equal to 2qd, the dipole moment. Okay, now if you continue this, so this will be the torque, okay, acting on the dipole if it displays in a uniform electric field. Simultaneously, if you have to find out the work done, we will just rotate by a very small angle. So the angular work done will be given by dw is equal to tau d theta. Now tau is, it's E P sine theta d theta. So this could be integrated, say within the limit theta 1 to theta 2. So your work done will be given by W is equal to EP minus cos theta from theta 1 to theta 2, that will be EP cos theta 1 minus cos theta 2. So this will be the work done due to, this is a potential, basically this is a potential energy of a dipole placed in a, this work done could be stored as a potential energy. Okay, so this work done could be stored as a potential energy in the, okay, when a dipole is placed in a uniform electric field. So this is what we have done in this particular lecture. We'll try to solve few of the numerical based on this what we have done so far in the next lecture. Until then, thank you.